Okay, so I hope now comes the interesting part with explosions and flames, and not the little bit more theoretical part. At first, I like to talk about explosion venting. I used to say explosion venting is the natural way of protection. If the vessel is not strong enough and you have an explosion, it will open somewhere and it will vent to the outside. So what we do with explosion venting is we try to control where the vessel opens, that it goes into the right direction and doesn't do things that we do not want it to do. Of course, we need certain information to be able to do explosion venting, and the vent area depends strongly on, of course, on the vessel size, which will define how much we have to vent to the outside. It also will depend on how easy the vent opens, so that it starts very early with the venting process. And of course, it also depends on the dust properties, on the maximum explosion pressure and on the KST value. What we must not forget when we do a vent area design is that if we have to vent to the outside, and that also should be a very important rule, we do not vent into buildings, into rooms, because that would create a pressure wave in the room. It would create a dust cloud if we have dust on the beams and everywhere. So, and we get, as I said before, it's only very little dust that we need. And then we would get a secondary explosion, which is turbulent, which can be devastating. And of course, also when we have elongated vessels, then we can have much stronger explosions, and therefore we have to take that into account, and that we also have put into the NFP 68 and into the venting standard in Europe, that vessel LOVDs influence the explosion, and we have to take that into account. Okay, let's look at a few explosions. So on the right-hand side, you see a silo, 236 cubic meters and 21 meter high. We did these tests after we had a certain, say, trial with explosions in large silos. We in Norway, during my time there, we were offered to use an existing silo complex that was being taken down, and we were allowed to do some experiments. In this, it was 8 times 500 cubic meter silos. The first experiment went a bit wrong. 4 of the silo cells were gone because the explosion was a bit too strong. With the remaining 4 silos, we were a bit more careful, so we managed to do 11 experiments. Then the remaining 4 silo cells also were gone. And that was financed at that time by the National Grain and Feed Association in the US. And then they asked us, can you build a silo that can withstand an explosion, so that we learn a little bit more? And that is the silo that you see here. And I think we did about 250 large-scale experiments in it to study what an explosion can do. And just to give you a feeling how it was an elongated silo, LOVD close to 5. And if we ignite close to the opening, and we always use the same vent area, If we ignite at the top, close to the opening, we had about 25 to 30 millibars overpressure. Not very much. If we ignited halfway down at about 10 meter, we would get not 25 to 30 millibar, but 250 millibar, which is already a little bit more. But if we ignite at the bottom of the silo, in this type of silo, we would get between 1.2 and 1.6 bar. No silo can take that. And that was a very new thing that we had to take into account. If you have elongated vessels, then you have to account for that, and all standards include this now. Here you see a filter explosion, a backhouse explosion. What you see there is, and that is very typical for backhouses, is when you use explosion venting there, you get huge flames outside. One of the reasons is that you have not only the dust atmosphere in this backhouse, but you have a lot of dust that is hanging on the bags, and that all will be blown out, and then you get an outside explosion. So therefore, you have to be very careful where you direct such a vented explosion from a backhouse. Okay, then we also had to do some, that is the silo again. We had, instead of going to the top with the flames, we had to go to the side. Reason for that, on the top, very often in silos, in the big silo complexes, you have a lot of machinery and things like that, and it's very difficult to use vents to go to the outside, and therefore the sponsors of the project wanted to see what happens when we do it to the outside. One thing already is clear: you have to look for the reaction forces. Otherwise, if you have a single silo cell, it will tip over because of the reaction force. Or you have to go and do venting to both sides so that the forces go away and that you do not tilt the silo. Okay, and then here you have again backhouse explosions. What we learned from that is if you have an explosion in a backhouse, stop the flow of air as soon as quick as possible. Otherwise you burn everything down because there's enough fuel and you really melt everything. We managed to, the first experiments where we didn't stop the flow immediately, we burned all filter bags, obviously, and we melted part of the roof that you have above there. And when we changed this and stopped an explosion immediately, or had kind of explosion isolation where a float valve was closed very quickly, we could do 8 to 10 experiments, explosion experiments with real filter bags before we had a number of holes and we had to exchange a few bags. That means an explosion is so fast, and if you have immediate stop of flow of the air, then your bags might not even go on fire, which is a big advantage, and especially for our experiments, because otherwise after each experiment we had one experiment one day and then 2 days to repair everything and put all the bags in place again. And after we stopped the flow, then this was much faster what we could do. What the experiments also showed, and I mentioned that before, that we get really huge flames to the outside. And that is something that also needs to be controlled. And in my PhD, I worked a lot with quenching phenomenon. So therefore I had the idea, why not quench this flame so that the flame doesn't come to the outside? And I'm a bit proud now to see that more or less all suppliers of explosion protection equipment use the so-called flameless venting now. And that is something that we developed in these experiments where we did try to control the flames. And here you see an explosion with such a quenching device. And here you have a free explosion. And the way it works, that you see here, that we have the vent that you use. If you do not use this device here, then the big flame will go here to the outside. If you have this device that is a little bit restricting the venting process, but it cools down the flame, and then the flame cannot go to the outside. And in certain applications, if you have relative small volumes somewhere in the factory, then this is a very efficient way in doing explosion venting in buildings. Free explosion venting always have to go to the outside. Here you could go and have small volumes that you vent into the building without all the additional things that you might need. And you probably also know, if you have equipment that needs to be channeled to the outside with a duct, then it has a very negative effect on your venting process. This has a much lesser effect. Okay, then I mentioned, do not vent into the building. This was vented into the building, but not only that. See the next picture. Do not have vents opposite to each other. If you have an explosion in this volume here, it will go and open this vent to the inside, and then you have an explosion in the second. In this case, it was 2 backhouses. So explosion here goes into this backhouse, and from the backhouse then, because of non-existent explosion isolation in all connected equipment that you had there. And that is not so good to have. Okay. Here we see a film where we use, and this is one of our test vessels. It's a 21 cubic meter vessel, and it's very strong, so we can do all kinds of experiments there. And what you see now is we just disperse the dust. You don't hear the sound. That is also quite good if you hear the sound. And let me see. And in the next experiment, we go from 250 grams to 1,000 grams, and that gives an even stronger explosion. You see that even the camera is shaking. And but what we also wanted to see is, if we do these experiments, what kind of vent area we have to use and what influencing parameter we have that could go and cause an additional problem here. And therefore here in the next video you see this in slow motion, and if you look at the roof there, then you see how the roof jumps up and down, even so everything is open. If you do something like that in your building that is closed, then something has to go, the walls, the windows, or whatever. And so that is something then one always should think of, that this is a problem. In the next video, that is the one that we already saw once, where you see then the effect on the roof, and it's fully contained, fully open. That was explosion venting. The next subject I'd like to address is explosion suppression. Completely different way of protecting. But what, and as I said, venting is a natural way of protecting, but you cannot always use it. And also, as I have mentioned before, explosion isolation comes into the picture, and that is much easier with explosion suppression. And that is what we like to look into here, that we see how when explosion suppression is done, how it works, and as I mentioned, in the end, the cost of installation and maintenance can, or most likely are higher than venting. But if you also take in consideration the explosion isolation, then you come more or less into the same region for the protection method. And it has some additional advantages. So what we do with explosion suppression is that at a certain pressure, or pressure rise, we activate the suppression. Typically we use the pressure detection, or detection how fast the pressure goes up, and then depending on the volume we know this only can be an explosion, and then we trigger and initiate the suppression, and instead of getting the full explosion pressure we get a so-called P-RED, the reduced explosion pressure. And that can be calculated, and then we try to stay below the vessel strengths. So in the next few pictures you'll see how explosion suppression works. If you have an ignition, like you see here, then the starting explosion will emit a pressure wave. And the advantage is that the pressure wave goes with 360 meters per second with the speed of sound. The flame speed, when you initiate an explosion, is something like 5 to 10 meters per second. So that means 5 to 10 meters per second flame speed as it spreads, and the pressure wave 360 meters per second. So that means we have a lot of, in that respect, a lot of time to do something about it. And what we do with explosion suppression is we activate, as the explosion grows, we activate with the pressure wave the bottles, and you see the suppressant entering into the vessel, and then it becomes a race between getting powder out and the explosion developing. And the maximum pressure we always get when the flame meets the wall. That means when the reaction surface is biggest. And therefore, with explosion suppression, we can achieve quite low reduced explosion pressures, which then go and protect the vessel from being blown apart. Also, over the last years, pressure detection has developed quite a bit. So nowadays we do not, as was done before, that we have mechanical pressure sensors, like you have here, or that you had pressure sensors that had 2 measuring cells to be redundant, which is a good idea, but one doesn't go and put the measuring cells just beside each other, because if you have product impact, then both cells get the signal at the same time, and that could cause a false triggering, which you definitely do not want to have in explosion suppression. So therefore, today, mostly it's 2 sensors are used, rate of rise sensors, and they are very stable, so false activations are practically non-existent anymore, at least to our experience. Okay, if we go and look in the back house here how this would look like. If we ignite if we have product impact and it goes into the vessel and hits one sensor, then this sensor, of course, will say, I have seen an explosion. But the second one says, no, I didn't. And then, of course, you do not activate the system. If you have an explosion, then you have, again, the pressure wave, which at the same time will meet both sensors. That means then the pressure wave goes, activates the two sensors, and then both, one says, I see an explosion, the other one in a certain time frame says, yeah, me too. And then the control is activating the suppression system to protect the vessel. There are different nozzles, and I don't have to go into that here. I just show them briefly. It's the powder nozzle and it's a T-plate nozzle that we are using, and that is being used in all types of industry. Here you have a big spray dryer with a fluid bed, and yeah, maybe also one special thing that I should mention here. Typically for explosion suppression, powder is used. And powder means so-called sodium bicarbonate, or most of you will know it as baking powder. So that means that nothing else but we push baking powder into the process. This will fall apart, it will form CO2, and when it falls apart, it consumes a lot of energy, and that is what makes our suppression. And at the same time, we premix the fuel that could be ignited with this powder, and then it cannot be ignited anymore, and therefore we quite often also call it advanced inerting system. That means we mix powder with the fuel with sodium bicarbonate, and then it cannot explode anymore. What we have done here, what you see here, that's a little bit different, and that is hot water, steam. We heat hot water, we heat water up to 180 degrees, and then we release it into, for example, into this fluid bed, and then it creates a sauna, and quite hot and wet, and explosions don't feel very comfortable in that, so they go dead. Some applications, of course, you cannot connect the bottle directly to this. Here you have big sieving machines in the wood industry, where you use flexible connections so that the sieve still can work, and you can manage to come in all the different areas where you want to have extinguishing powder. In the lower part, there's a plate here in between, and you bring the powder to where it is needed, so that you have this advanced inerting effect, so that the explosion cannot propagate. Okay. This one, yeah, okay. So what you see here is an explosion in a 145 cubic meter vessel. And I have to do a little bit of talking now, because we introduce dust in the end of the vessel, and then we just let the explosion go, and this is a high-speed film to film how the explosion behaves in this 145 cubic meter vessel. You see a little bit yellow here. It will disappear again, and it takes a little bit longer time until it comes up again, and then the flame breaks together. So this is only an explosion, no suppression. And then in the next film, you see the difference. Just watch and look at the time it takes, because now still the camera is completely full of light because of the burning material in this vessel. And then slowly you see, now it comes up again, and now the flame will break together, and then you can look into the vessel and see that there's still a lot of burning material. So we have really filmed into this vessel, and you see the flame is now collapsing, but what you still see is there's a lot of flames everywhere in the vessel. If now you have a system, a transport system that blows in additional dusts, then of course you will enhance the explosion again, and you will feed the explosion to further burn. And also if you have something like that in the filter, obviously the filters will burn away because you have a big filter fire, and this is what happens. So if we then look into the next vessel where we have, and we use hot water in this case so that we can see what happens, and then you have seen how long it took now until, and it's still burning here. And now we look into the next explosion where we use the hot water. It will come from the left side here. There you see the hot water comes in as a suppressant, and that is what happens when you suppress an explosion compared to what you had before when you didn't suppress it. And as you also can see, there is no flames afterwards. Okay, an important subject, I mentioned it already. This was a filter in the wood industry, and if I'm not taken very wrong, it was somewhere here in Argentina. And the filter had explosion vents here. What turned out is the explosion vents didn't have time to open. The whole wall just blew away. We checked it, and we found that the vents were designed properly. So how can it happen that the explosion is so fast that the vents didn't have time to open, that just the whole wall blew away? We did have explosion isolation, and the explosion didn't start in the filter, but the explosion ran from another volume into the filter. And easily you can get much, much, much higher pressure than if the explosion accelerates into the filter. And as I mentioned before, a typical explosion, if we had a dust cloud in here and we ignite it, it has a flame speed of 5 to 10 meters per second. So that means if I start running, and maybe the few here in this area, they would manage to get to the door before the explosion gets them. If you allow the explosion to enter this room from somewhere else, through a duct, through a pipe, it's not 5 to 10 meters per second, but it can be 500 or even more meters per second. And then you cannot go and control it anymore. Then you have an explosion that is uncontrollable. So therefore, explosion isolation, one of the most important things that needs to be done when you want to make your plant safe. And if you start to upgrade your safety, you first start to think about explosion isolation. Forget about explosion protection for a moment. First is isolation, and then you identify the volumes, the areas that could endanger people. And the third step would be to see what kind of equipment do I have that could cause complete stop of our plant or production. So if you have one main elevator, that is the only one that can take product or distribute product. If you have a distributor somewhere that is feeding into many different silos, That are the things then that one looks at in order to keep the plant running. But as I say, explosion isolation first, the most important thing. So if you have two vessels that are connected to each other and you have an explosion in the first vessel, vents is designed properly so the vessel will vent to the outside. And as I said, if you allow the explosion then to accelerate in the duct, you start pressurizing the second vessel, which means that your resulting pressure is much higher. But what you also do is you get a so-called flame jet ignition, which goes with high speed into the second vessel, and then the flame doesn't slow down again to 5-10 meters per second. It will continue with its 500 meters per second and go into the second vessel. And that is really a problem then. So then, as I said, then no protection method is working anymore because it's all for the same vessel. So therefore, isolate it to make sure that an explosion cannot propagate into it. Okay, we have seen this film before. We see it once more because I wanted to show something else, and that is the explosion with the 1,000 grams per cubic meter. And if we then go and look at the next video, which is going into slow motion. We see that the flame comes out, and then we look at the vessel from this side in the next picture. Okay, and what you can see now is we have two small openings, which could be ducts going into the vessel, and on the other side we have the explosion that we already have seen before. And this is a slow motion high-speed video now, and you see that a little cloud comes out, and then we ignite, and then the explosion will go into the ducts, which we have taken away, and it will be vented to the outside. But just look at the force, how it is pressed into the two ducts. In the end, you see the explosion, but the two ducts, with high speed, they press the explosion into the duct. And then it continues to accelerate in the duct. Oh, sorry. I think then we should go and do this again. I just go and... Okay, so we look at this again. So that is the explosion that we just went to the outside. And then in the next picture, we open two small openings, which could be a duct to the outside. Yeah, you see that I get excited about this. And to the side we have two small openings which could be ducts, and the explosion presses the flames into it and accelerates the flames, and in the end on the other side you see the vented explosion going to the outside. Here now we have ignition, and you see that the explosion starts suddenly to press into the ducts, causes a lot of turbulence, and it is vented to the outside. But the important thing is the force that you see, how it blows into the openings and then causes explosion propagation. Okay, and then something like this happens. You have two silos beside each other, and both burn. Any idea in which silo the explosion started first? In the right one, of course, because what you see here is there's even vent panels that didn't open. So you had a relative weak explosion in here. Then it went through the pipe and ductwork into the second, and then the second one really got a lot of damage, while the first one didn't get that much damage. only everything burned down, obviously. And so that was also because of explosion, not to have explosion isolation. There are different methods in order to avoid explosion propagation. One would be explosion diverter. There are float valves and all kinds of things to stop an explosion from propagating with high speed. Explosion diverters are no safe explosion isolators, but what they do is they take the force out of a system. So if you have an explosion diverter between two vessels, what happens then is that the explosion comes from one vessel, goes out here, it goes to the opening. It could be that it can propagate here, but it cannot speed up again if this one is close to the second vessel. And that's a very simple method of isolating the effects. And then if the second vessel is protected by explosion venting, then it will work again, and you do not get this devastating flame acceleration. So the principle of active explosion isolation is that you need a detection, you need something quickly reacting, so different detection methods are used there. That can be pressure detection, as we use for explosion suppression, but it can also be an indicator, an vent indicator for vent opening, or it could be infrared flame detection. Normally, you require 2 to 5 meters distance from the first volume to safely isolate the explosion from propagating into the second volume. Just a few pictures of typical active explosion isolators, and of course also hot water or dry chemical. The flame extinguishers can be used for isolating an explosion, where you use pressure detection and then either a bottle with a powder or hot water. So, conclusions for this part, before I give a few other application examples, is about 70% of all organic dusts handled are explosible. So you have a good chance that you have explosible dust in your facilities, and that means if you do not have any information about your products, then you have to do some tests for flammability. That means how easy is the dust ignitable, and you also have to go and measure the explosion characteristics, which mean what kind of consequence can an explosion have, how high is the P max, and how fast is the pressure rise, because that defines how quick you have to go with your suppression or your venting system. Assess the process plant. That means you have to go and make an evaluation. Where do you have explosible atmospheres, and what kind of potential ignition sources you have. And that is very easy if you first go through the plant and make a zone classification. But be careful with this. In Europe, many companies, when we got the law that one had to make a zone classification, then many companies, they decided, okay, all this we make zone 20 and all this is zone 21, without going into detail. But it then took a lot of time to go back on that again, because zone 20 requires certain type of equipment, certain type of electrical classified equipment, and that can be very, very costly. So therefore, one really should go into detail and say, okay, what do I have here? Do I have, say, an explosive atmosphere that is continuously there, or is it only a very short time there, and that will influence then what kind of protection methods you can use. And of course then we have to look into explosion prevention and protection. Various options are available, often designed for particular dust. Also, if you have a multi-purpose equipment where you use different dusts, first get a picture on what kind of dust you have and what KST values it have, because otherwise it can turn out that you could not use this and handle this dust anymore in your equipment. Just a very few practical things now, and this we also have done in NFPA, based mostly on these 250 filter experiments that I talked about earlier that we did in Norway, because we found that in a filter you do not need that much vent opening, because you have filter bags that consume energy. You have the clean air side where the explosion pressure can be dissipated to the clean air side, and therefore we found that when we look at the filter, let me see, if the vent is below the filter bags, then we only have to protect this volume. We put an envelope around these bags and just subtract it completely, because it doesn't contribute to the pressure that you have in the filter. If you have the vent behind the filter bags, then it's not working. The venting is not working so good, and that means then one thing is you have to use the whole volume for protection, and then it still could be too little. So you really have to consider these bags that you have, can they completely block the venting, because then you have to do something about that. And a third method would be that you have a free volume on the side of the bags and some kind of barrier that the bags cannot be pulled into the vent opening, and then you have to use the whole dirty air volume. So that means here you can subtract the whole thing here, the whole volume, and you only use this volume here. Here you use the complete dirty air volume, and here you have to use the whole filter or volume for vent area design. Sometimes people are talking about partial venting. If you, for example, have a dryer or other equipment where the dust cloud only is in the lower part of the vessel, then you have a good chance that you do not need to take the full volume into account. But if you put your vent on the top of this vessel, even if you have only dust normally in the lower part, but in an explosion you push the dust cloud into the upper part, and the only thing that happens is there's less dust that goes to the outside and creates an explosion outside. That means you still have to use the whole volume. But if you manage in a dryer, for example, to put the vent to the lower part where you have the dust cloud, then you can more or less divide the volume into two parts, and you only have to consider half the volume. Or you get half the P red. That means you need half the vessel strength. Okay, here one picture which happened in Germany. It was a flour mill. 14 people were killed. 17 seriously injured. The damage was, as you can see here, damage was more than 100 million euros. We have, in the aftermath, calculated how much would it have cost to protect this installation, because the explosion propagated from different rooms and became worse and worse, so it started originally here. It would have cost about 500,000 euros, 500,000, to protect the complete plant, that nothing could have happened. Now it was 14 dead, 17 seriously injured, and the damage was 100 million, not 500,000. So that is the difference between do proper explosion protection and don't do anything. Elevator explosion, just a few words to that, because we have frequent elevator explosions which very often turn into secondary explosions, because the elevator opens, flames comes out, goes into an area where you have a lot of dust. You do not have explosion isolation, so the flames propagate through the elevator into the silos, and you get these huge silo explosions. If you look at how to protect an elevator, of course, the easiest way is to say, explosion venting. Yes, you can use explosion venting for elevators, and as I said, it's the natural way of protection. But you still need explosion isolation. And as you can see in the experiment here with the elevator, if you have frequent vent openings, you have flames everywhere. And these flames also is pressure, which can create dust clouds and create secondary explosions. But what it also does is that afterwards, after an explosion in the elevator, you have to exchange, when you do explosion venting, you have to exchange the belt, because it will burn down. You cannot use it anymore. It will stop your production for quite a while, but it will also damage the belt and everything that is in it. And you still need explosion isolation. So therefore, in many cases, if an elevator is outside, yes, then that is a nice and easy way to get rid of the flames, but the elevator will be damaged and it has to be repaired. And if you then consider the downtime and the price, then you find very quickly out it would have been better to spend a little bit more money for explosion suppression, because in explosion suppression, as a rule, you do not damage the belt. And that means in a very short time you could be in production again. And many companies in Germany or Europe, what they do is, at least the elevators that they have identified as essential for operation of their installation, of their company, those elevators they suppress, because they say then downtime is very little. We can immediately, more or less immediately go and start to go back into operation again. And of course, we do not have any explosion propagation. This you have seen before, the big flames that come out of a filter when you have a filter explosion, and this flameless venting. So that is always that one has to consider. What I also have mentioned here, the difference between short vessels and long vessels in vent area design, that has to be taken into account, that with long vessels explosions become much stronger, and you have to consider the L over D to make sure that you have the right vent area or the right vessel strength. Okay, I just hop over this because that is just going into little equipment, because I like to, before we end, I like to look at one more thing. Your job. Do an open-eyed walk through your installation and ask yourself a few very simple questions. One is, where do I have enclosures with combustible dust? You all know that. You know your equipment. And you can answer this. And also for rooms, do I have 1 millimeter or above that deposit on the floors? Because that would be sufficient to have an explosion. The second question that you ask yourself is, if I had an explosion in this enclosure, could the explosion propagate into another connected vessel? If yes, you're in trouble and you need explosion isolation. And the last thing, would the enclosure be able to handle the explosion? If not, are the consequences such that I can accept them? Is the vessel somewhere out where nobody could get endangered and things like that? Then I can accept that. If not, then I need to do some explosion control. Let me just look very quickly at the last thing, because that is also a very important example. If you have, and many of you, I'm quite sure, already have had some kind of fire in a storage facility. And even today, I heard that fire brigade doesn't always know how to handle fire in a silo. And this is a very typical example for this. It's a 50,000 cubic meter pellet silo. For after the sugar production, they produce these pellets for animal feed. It's from sugar beans. And here you see the silo complex. And this silo here went on fire. It's 58 meters high and 32 meters in diameter. Quite a big thing. What you also see is that we have, unfortunately, quite often in Germany, that we have houses right around this. And I spent Christmas and New Year Eve from 1999 to 2000. I spent there because they had this fire and they did a lot of, say, not so good things that made the fire worse and worse. Here you see the fire from the silo from the inside, and what you also see is here, this is the pellet levels. And they had a problem in the transport system here. This problem caused that burning material fell into the silo. No explosion, nothing. And it was a fire which is normally quite easy to handle. It was a fire on the surface here. And that could have been handled quite easily. But what the fire brigade and the people decided is to empty the silo. And if you know how a silo like that has different openings here in the bottom, I need to take this one. Here, where you empty the mass onto a belt, then you get a so-called funnel flow, which means if you take the mass out here, then the material will go down here, and you get kind of a funnel, and the material from the top will go into the mass here. That means the fire brigade, after 4 or 5 trucks full of material, they had fire here. What they did is, okay, they stopped doing here, And they took the next opening and did the same. And suddenly, after a while, we had 25,000 tons of product on fire. And you can imagine what kind of fire that is if you have 25,000 tons of material burning. So it looked not so dramatic, but it was quite dramatic. And we tried to control the fire by inerting from underneath, because we had quite a big, strong draft through the mass, and fresh air would come into it all the time. So that means we stopped the air going into it and enhancing the fire. And we put carbon dioxide from the top, dry ice, to cover the volume, which still was something like 20,000 cubic meters, to cover the volume so that we could not get a dust explosion. Here you see the camera that we used to measure the temperatures outside of the silo, and you see where the fire is, all the red ones, that is where we have very high temperatures. And here you see the temperatures that we experienced. So that means below the roof floor we had about 280 degrees, and on the pellet surface it was 400 to 800. So it was big fire. What still gives me a goose skin is everything that we did, the nitrogen and also the CO2 from the top, it made sure that we could not get an explosion. But New Year's Eve was coming up. And that caused some concern because we didn't want people to use fireworks. And the worst thing that happened then was we had a lot of gas measuring equipment, because these pellets, they contain still a lot of sugar. And the fire brigade also had used some water. So that means we initiated a fermentation process in there, and we knew that this fermentation process, it can stop at any level and produce something that we didn't want to have. And here we got it. So we had inside, we had methane development. We had, and that was the worst thing, we had, sorry for the German words, so we had methane and we had hydrogen in it, and hydrogen concentrations above the lower explosive limit. So now suddenly we ended up in not only having a pellet silo on fire, but we had big concentrations of hydrogen gas, which is very easy ignited, and we had methane in it. And as I said, New Year's Eve coming up, where people use fireworks, which we didn't want them to. And what we then finally used was we used some kind of starch with water. It's the glue that you use for putting wallpapers onto a wall. And we covered the top of the silo with about 1 meter layer of this starch to make sure that we got the draft out of this process, and that we didn't create the gas concentrations in the empty volume, to make sure that we couldn't get a gas explosion. And when I arrived just before New Year Eve, we were in the explosible range, but then it took a few hours with all the inert gas that we could blow in to make sure that the fire was controlled. Then finally we found that because of the temperatures, the silo had been damaged so much that we had to take it down. But we still had 25,000 tons of burning pellets in the silo. But we couldn't wait until the fire eventually very slowly stops because the new season was already coming up, and latest in, this was New Year, and latest in August, September, a new silo was needed. Therefore, we decided that we break the silo down while the fire is still going on, but it was protected, contained through this layer of starch, glue, I would say. And then the silo was broken down. You see here a specially built machine that was between inner and outer silo and broke down pieces like that. One piece is about 30 tons that falls down to the ground when they cut it. And here you see the job is more or less done. Silo is just about empty, and we got rid of all the pellets. They were brought to a burning facility used as energy production. And here you see, in time, the new silo, which is something like this now, not this type of silos anymore, but this silo, and now they could go in with equipment and go and do this. Okay, but this is just an example of how a silo fire can be handled, and what I've heard many times now is that, and we have seen that in Norway, during my time in Norway, that fire brigades need to be trained, and in Norway we had courses for fire brigades how to proceed if you have a fire in the silo. First go and inert the empty volumes so that you do not get an explosion. And then you can try to find out how you best handle this, but do not just go and empty the silo, or water doesn't help, because the water finds its way, but it doesn't find the way to the flame. Okay, I think I like to finish here. And the lessons learned, I've written them down here. Firefighters need to be trained, and the heat and smoke relief doors, which used to be a law in at least Germany, that a big silo, they needed to have escapes. They caused a problem because of that we got a big draft, and it enhanced the fire, and it didn't help at all. So therefore, now we don't need those doors there anymore. And before starting to fight such a silo fire, assessment is to be made. Where is the fire and how did it start? So that you do not bring the fire into all the material. It would have been much, much easier to fight the surface fire if it would have been done in the right way. But in this way, it was not possible. And then, of course, the use of water must be the very last resort. And if you have products that could undergo fermentation and produce gas, then you also have to consider not only dust explosions, but gas explosions. Okay, I'd like to finish here, and I'd like to thank you for your attention. And if you have questions, you may send them to me, but you can also ask a few questions here if you have some.
This question a question about venting panels. Do you have experience with venting panels that are not rigid? They are sheets of PVC or polyethylene.
Yes, in industry, quite often you find panels like that. The problem really is that you do not know the opening static opening pressure, which can be a problem because you need to design proper vent area. You need to know exactly at what pressure the vent will open. And also it could be that it goes too slow. And one more problem is that it could fly away. And definition of safe venting in the European standard and also in the NFPA is that no fragments of a vent should fly away because they can hurt people, but they also can go and, in our silo in Norway, we used plastic things and so on because we didn't want to buy new vents every time just for the testing. And yes, we burned about 20,000 square meters of wood and trees because when we did the side venting that I showed before, then some of the plastic vents flew into the grass, dry grass and wood and put it on fire. And so therefore, recommendation is that one should use proper vents and make sure that parts cannot fly away.
Thank you.
Thank you.
Una pregunta.
You work with physical testing. How did you experiment with simulation models with this kind of problems using software for simulations?
Yes. When you do explosion experiments, then or also when you want to have vents or explosion suppression certified, then you have to develop a model which can calculate this. There is one lag that sometimes is forgotten, and that is, and we have seen that when we used our 145 cubic meter vessel now. One thing is, of course, a big vessel is much easier to handle than a small one, because in a small vessel, explosion is very fast. But what we found is that also in the certification of our suppression system, in the so-called notified bodies that we have all over Europe, and also maybe FM in the US who do such certifications, tests always seem to be done in closed vessels. In industry, we hardly have closed vessels because they have an inlet, they have an outlet, and all things like that. And we right now, we have contracted a company in Norway called Gexcon. They use FD modeling to model, and that is also where I was involved. They model gas explosions and also have started to model dust explosions now. And we have come to an agreement now that we provide them with all the data that we have from our big test vessel, because this test vessel is the largest, biggest that you have in the world in the moment. And they will go and put this into the model. But what I already can say is if you have explosion venting or also explosion suppression, that only small openings on the vessel have a big influence. And you remember what I presented, the pressures that we got in the silo. If we ignite on the top and the flame just burns down, it was very small pressures. If we ignite on the bottom, very high pressures, because the flame can kick off and accelerate into the volume. But if you have somewhere in the bottom or somewhere small openings, then this kickoff doesn't happen so fast. And what we found is that if we compare pressures where we only have small openings and where we have no openings, the reduced pressure is about half. And that accounts for venting as well as for suppression, that the flame doesn't accelerate that much, especially in elongated vessels, and that we get much lower pressures. Yes, and to your question, yes, there's a lot going on in CFD modeling to try to exactly calculate what kind of pressure development you have. Okay, thank you very much. Thank you.